For problem 29, the table below shows the number of pounds of apples grown last year in 4 cities. Each whole apple on the graph represents 1,000 pounds of apples. According to the graph, what fraction of the apples grown in all 4 cities were grown in Appleton? So one of the things you should know about this prompt is that, looking at this table here, we have the city, Golden Hills, Red Falls, Appleton, and Shady Acres, and then how many apples were grown. They're using these apples to represent 1,000 pounds of apples. But because we're going to try to figure out the fraction of apples that are grown in Appleton with respect to all apples grown in this area, we really don't even need to factor in this an apple represents 1,000 pounds. We'll see in a minute. Anyways, if we're going to find the ratio or fraction of apples grown in all 4 cities in which were grown in Appleton, essentially we're going to do that by finding how many apples were grown in Appleton divided by total apples grown. So if we count, we have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And notice that we have a half here and a half here, so that would be a total of 12. 12 apples in the table here. Now again, this 1,000 pounds per apple is really not necessary. We can use that 12 value here in the denominator. Now how many were grown in Appleton? Well, we have 1, 2 and a half, 2.5. 2.5. So the fraction they want us to come up with is 2.5 divided by 12. 2.5 apples out of the 12 apples total were grown in Appleton. The problem is that if we scan our choices here, A, B, C, D, and E, we'll realize that we don't have any fractions with numbers that have decimals on the numerator. And that's because typically fractions are simplified to the point where we're using whole numbers or integers in both the numerator and the denominator rather than numbers with decimals. So how do we convert or find an equivalent fraction to 2.5 divided by 12, this fraction right here? How do we find an equivalent fraction that is in terms of integers, not numbers with decimals? Well, remember that if we have a fraction like 2.5 divided by 12, if we multiply the top and the bottom, the numerator and the denominator, by the same number, n, we'll find an equivalent fraction. In other words, in this case, if we have 2.5, a way to make this 2.5 into a whole number or integer would be to multiply it times 2. In other words, n would be 2. So 2.5 times 2 is 5. Then 2 times 12, we have to do the same thing to the denominator so that we're really obtaining an equivalent fraction. 12 times 2 is 24. In other words, the fraction 2.5 divided by 12 is equivalent, is exactly the same as 5 divided by 24, because all we did was multiply both the numerator times 2 and the denominator times 2, and that'll always give us equivalent fractions, as long as the number used both then on the numerator and for the denominator is the same. So now when we look at our choices, we realize that we have a match. Choice A, 5 out of every 24 apples were grown in Appleton. Now, if you're thinking that because we didn't use the 1,000 apples measurement there that is mentioned on the prompt, and then we cheated somehow, notice what happens if we do 2.5 times 1,000. We're going to get 2,500 apples grown in Appleton, and then we had 12 on the denominator for the total number of apples grown, so 12 times 1,000 would be equal to 12,000. So this is the fraction we would be working with, 2,500 divided by 12,000. Now, again, we would need to simplify this fraction. So there's a little trick here when you have both a number and a number on the numerator and the denominator, and if they're ending in 0 and they don't have any decimals, what we can do is we can start canceling zeros from right to left. So we'll cancel the first 0 from the numerator and from the denominator. The next one, and that's as far as we can go. So we end up with 25 divided by 120. Now we need to simplify this again, and you should be able to see that the number 5 divides evenly both the numerator and the denominator. And again, just like on the previous method, a way to find equivalent fractions is to multiply both the numerator and the denominator by the same number. Well, with division, you also obtain an equivalent fraction. In other words, if I divide both the numerator, in this case by 5, and the denominator by that same number, I'm guaranteed to find an equivalent fraction. So 25 divided by 5 is 5, and then 120 divided by 5 is 24. And that gives us the simplified fraction, which matches choice A again. So you can see that this... For problem 29, you have to count the total number of apples. That's going to be the total number of apples that were grown in all 4 cities. And so there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, because there's a half and a half. So that's a total of 12. And because each apple represents 1,000 pounds of apples, so 12 times 1,000 gives us a total of 12,000 pounds. We really don't need to do that, by the way, but we could just use the fact that everything is proportional. But I do want you to understand what the prompt is asking and what you would need to do to find the total number of apples, say, grown in all 4 of these cities. Now that we know the total number of apples grown, they want us to know what fraction of the apples were grown in Appleton. Well, Appleton has 2.5 apples. So 2.5 apples means 2.5 times 1,000, which is of course equal to 2,500. So out of the 12,000, 2,500 were grown in Appleton. So you could do 2,500 divided by 12,000 like this. But the calculator is going to give you a decimal number. And what you really want to do is you want to keep it in fraction format, because when you look at your choices, they're all fractions. So remember the TI, very simple. You go to math, and then you go to frac for fractions, and then you say 1, enter a numerator, denominator, enter a fraction. So what fraction are you going to enter? The 2,500 and then the 12,000 on the denominator. When you press enter, remember the TI is going to simplify this for you. 5/24. For problem 30, what you need to know here is that if segment AD measures 25, AC 19, and BD 14, clearly AC and BD are overlapping. And so if we do 19 plus 14, we got a total of 33. And because the segment AD actually measures 25, so if we subtract 25 from that, we get 8, and that is the measurement of the segment BC. So if you do the math there, you'll be able to realize now what A, B, C, and D measure, and when you add those, you will realize that they do add up to 25. For problem 31, it reads, what is the x-coordinate of the point in the standard x, y coordinate plane at which the two lines y equals negative 2x plus 7 and y equals 3x minus 3 intersect? So the first thing we should know is that line 1 is y equals negative 2x plus 7. Line 2 would be y equals 3x minus 3. Now, we should notice a couple of things. Both of these are in slope-intercept form. So the first part here, the coefficient of the x term would be the slope value. And then the adding or subtracting value, the independent term, corresponds to the point of intersection, the y-intercept. The y-intercept. So the way it works is, for example, with line 1, with y equals negative 2x plus 7, if I were to draw the x, y axis, the plus 7 is telling me that it's crossing at 1, 2, 3, 4, 5, 6, 7, at 0, 7. That's the y-intercept point, because it's the y-axis and it's the point where this line 1 crosses the y-intercept. When you have a point on the y-intercept, you'll always have a next value of 0. It's the y value that is determined by the whatever you have here. So on line 2, what would be the y-intercept? Well, it's the same x value of 0 because it has to be on the y-axis. So x will always be 0 for the y-intercept point. But you see the subtracting 3, that means this is a negative 3. So for line 2, we know that its y-intercept is going to be at 0, negative 3. We'll plot that in a second. Back to line 1. So now that we know that the y-intercept point is 0, 7, we can then look at the slope value of negative 2. Now slope, which is equal to m, can be seen as being equal to rise divided by run. Now the value is negative 2. Negative 2 divided by what? Well, negative 2 is the same as negative 2 divided by 1. Think about it. So whenever you have a slope that is not in fraction form, you know that the run value, the denominator, is going to be equal to 1. Okay, so what do we do with this negative 2 over 1? Well, first it would be nice if we had some sort of a scale for the x-axis. It doesn't have to match the y-axis scale, but, I'll just try to match it a little bit. So here we go. We want to be as consistent as we can. Now, of course, this is just a sketch. And we're going to see on the TI how you can solve this, and graph it even. But at the end of the day, if I do a reasonable job, I should be able to work with this. Okay, anyways, so back to the slope for line 1, negative 2 over 1. So you can see that the line 1 has a y-intercept of 0, 7, which is that point. So you can only use the slope value rise over run if you start on a known point of the line you're working with. In other words, I couldn't start anywhere on this graph and use the slope information. I need to start on a point that I know belongs, in this case, to line 1. Well, the only point I know that belongs to line 1 is this y-intercept, the 0, 7. So if I imagine standing on that point right there, and then I look at its rise value and run value, what I can do is I can rise negative 2 from this point. Which means if I'm going to rise negative 2, it means I'm going to go down. If it was a positive value, I would go up. So down 2 means 1, 2. Now I'm at positive 5 on the y-axis. But I'm not done. I can't stop because there's a run value of 1. The run value is positive, so when the run value is positive, you move to the right. And that means that if I'm standing at x equals 0, moving 1 to the right would land me here at x equals 1. So I have a second point for this line. Now I can just connect, because I know that this is the linear equation, the equation of a straight line, and if I connect these with a straight line, I get something like this. So this is line 1. Now for line 2, I can do the same exercise. Again, we know that its y-intercept point is 0, negative 3. So that would be negative 1, negative 2, negative 3, about there. So that's the y-intercept of line 2. And then its slope value is 3, meaning m is equal to 3 divided by 1. Remember, we need a run value, and when you have a whole number as the slope value, the coefficient of the x term, you simply divide that by 1, and there you go. You have your rise over run value. So notice that this time the rise is positive 3. So because I'm working with line 2, I'll stand on a known point for line 2, which is this 0, negative 3. Rise 3 would be go up 1, 2, 3. Notice that I would be temporarily standing on the origin there, the 0, 0. But then the run value of 1 means I need to move to the right 1 spot. So I move to the right and I land here at 1, 0. Now if I connect these two lines, these two points, with a straight line, because again, these are linear equations of lines, what you will get is something like this. And there's an intersect point. Now, unless you do a very, very good job of graphing, it's going to be very difficult to graphically solve this. Although if we, eyeball this, it seems like our answer is about x equals 2. I mean, look at when x equals 2, what happens? It seems to be the point where these two lines are crossing. Now, I didn't do a very good job of graphing this. I should have used maybe a ruler and used evenly separated points for the scale on the x and y axis, etc. And then I could, reasonably get a very good close approximation of the graphs and find the answer graphically. But even with this sketch, I can kind of see that x equals 2 seems to be the right answer. And look at choice D. There's a 2 right. We could take this x equals 2 value that we think works and plug it into both equations and see if we get the same y value, the same output. So for line 1, it looks like this. Y equals negative 2, parentheses, plug in the x value I want to evaluate, so times 2 plus 7. If you do the math here, you get an output, a y value of negative 2 times 2 is negative 4, and negative 4 plus 7 is equal to 3. So that's the output value. And if you see the graph, you know, I'm off a little bit because I'm not doing a very good job of graphing this, but it is kind of at the 3 spot. So it's a reasonable approximation. Anyways, let's go to line 2 now. Plug in the value of 2 again. Its equation is y equals 3x, so that's where we plug in the 2 that we're testing, and then minus 3. Well, this is equal to 3 times 2, which is 6. Remember, PEMDAS, order of operations. And then 6 minus 3, which is, of course, 3. And we notice that for both line 1 and line 2, using an x value of 2 will give us the same output. In other words, they share the same point. It's the point of intersection, 2, 3, for both of these lines, line 1 and line 2. So we found our answer. Now, if you don't like the graphic method, there's also the algebra method. And we can solve doing the following. So I'm going to first erase here. Just clean this up a little bit. So what we can do is we can take both of these equations and say, okay, so from the first equation, line 1, y equals negative 2x plus 7. From the second one, we know that y equals 3x minus 3. So what we can do is we can take the value of y from the second equation, which is 3x minus 3, and plug that, replace the y from the first equation with 3x minus 3. That'll give us the following expression. 3x minus 3 is equal to negative 2x plus 7. Why am I doing this? Because notice that now I have one equation with a single variable. And why am I allowed to do this? Because I'm trying to find the point of intersection. In other words, the point where both line 1 and line 2 have the same solution pair, which is the same for the same input value x, you get the exact same output value y. So you are allowed to say that 3x minus 3 is equal to y from the second equation, so replace the first y from equation 1 with 3x minus 3. Now we need to do a little algebra here so that we solve for x. Notice that the negative 2x term here on the right side could be sent to the other side adding. If we were to add both sides by 2x, it'll eliminate the negative 2x from the right side, which is what we want, and it gives us a 3x minus 3 plus 2x on the left side. Combine like terms, 3x plus 2x is 5x, so you end up with 5x minus 3 is equal to 7. The next step is to add 3, because it's subtracting here. So if you add 3 to both sides, you end up with 5x is equal to 10. The last step is to divide both sides by 5, so you end up with x is equal to 2. What is this saying? Well, this is telling you that for this system of equations which we created by saying that these two have the same xy coordinate, which is what we want to define, the intersect point, we now know that at x equals 2, we are guaranteed to have the same y values from both of these equations. So this is the point of intersection. We wouldn't know what the y value is, we just know what the x value is. If we wanted to know the y value given this x value of 2 that we found, we would then just plug this x value into either line 1 or line 2, replacing the x with that 2 that we just found, and it would give us a y value, the output. And we already did that from the previous method, and we know that the y value would be equal to 3 in both cases. And so 2, 3 is in fact the point of intersection for these two lines. And again, choice D would be correct. On the TI, you're going to see that you can actually graph the two lines, and you can trace the graph so that you can visually see where the point of intersection is.
Problem 31, we can do two things. The first one is to plug in the answer, x equals 2, that we think is correct based on that sketch that we did. So it would look like this. Plugging in x equals 2 on the first equation, y equals negative 2x plus 7, would be negative 2, open a parentheses for the x value that you're plugging in this case the 2, and then add 7. So press enter and we get an output of 3. So x equals 2, y equals 3. Now we plug in the same x value of 2 into the second equation of a line, which is y equals 3x minus 3. So it would be 3 parentheses, a 2, and then the subtracting 3. And we get the same output. So that means that for a value of x equals 2, because we get the same output on both equations, it means that it is the point of intersection. The other way to do this using the TI is to go to, over here you have y equals, window, zoom, trace, graph. These are graphing keys. So if we go to y equals, we can actually key in the equations of the lines. So the way to do that is to, on y subindex 1, that's the first equation, we would key in negative 2, x is this key right here, x, and then plus 7. And then if we use the arrow keys to navigate to the next y subindex 2, that would be the second line. We want to graph both on the same screen. We enter 3x minus 3, and then we press the graph key over here. What you're going to see is something appear on your screen which may or may not be exactly what you need. One of the things that you have to be careful when graphing on the TIs is you need to go to window, press window, and you have to make sure that your x min, x max, y min, y max values are reasonable based on what you're graphing. In this case, let me give you a glimpse of the xy axis by choosing an x min value of say negative 5. And then scroll down, an x max value of 5. And then for the y min, let's do the same thing, negative 5, and y max of positive 5. What am I doing here? I'm telling the calculator that I wanted to start with an x value of negative 5 on the left-hand side and go all the way to 5 on the right-hand side. That's on the x-axis. And then for the y-axis to start at negative 5 and then go all the way up to positive 5. Look what happens when I press graph. You can now see the xy axis. And it's graphing both lines. Now I can use the trace function here. It's a functionality of the TIs. If I press trace, I'm actually going to be able to move on the graph of one of the two and actually find that point of intersection. So if I move over to x equals 2, look what happens. 0.9, what? There's the cursor. So you can see that I'm at x equals 2.045, whatever. The output is y equals 2.9099, whatever. What that's doing is approximating a little bit. You can see that if I go back one with the arrow key to 1.96, I get an output for y of 3.06. So it's not going to be the precise way of figuring this out because it depends on the window that you've set and the scale and you know, the graphs, etc. So it can be complicated, but graphing the two, you can see right away that at x equals 2, 1, 2, at x equals 2, and then of a height of 1, 2, 3, 2, comma 3, the lines intersect. And again, because the choices were in fact, you know, 1, 2, 3, 5, 10, 1 is not the point of intersection for these lines, 3 clearly isn't, and 2 is. So, you know, even though this is not giving you the exact answer, it's very close to the exact answer, it's usable.
For problem 32, it reads, for all pairs of real numbers s and t, where s is equal to 4t minus 7, what is t equal to? So essentially, we have s equals 4 times t minus 7, and they're asking us to solve for t. So this is just pure algebra. To solve this correctly, remember, equations are like scale balances, in the sense that, you know, if you have, say, if you put 5 kilograms on one side, you better put 5 kilograms on the other to keep things equal. What the lesson there is that whatever you do to the left side of an equation, you better do the same thing to the entire right side to keep things always equally balanced. All right, so looking at this simple equation here, we're trying to solve for t. So we first have to get rid of this subtracting 7. To get rid of that, we would add 7 to both sides of the equation, again, with the idea of a scale balance. So adding 7 to both sides leads to, on the left side, s plus 7. And then on the right side, 4t minus 7 plus 7, this is 0. So you end up with 4t minus 0 or plus 0, which is simply 4t. And then the last step, of course, is to take this 4 that is multiplying the t and send it to the other side dividing. Or divide the entire both sides by that number 4. What will happen on the right side is that the 4 times t continuous multiplication link, and then a 4 on the denominator allows me to cancel the 4's. They become 1. 4 divided by 4 is 1. 1 times t is t. Okay, I've isolated the t, which is what I was solving for. If you're bothered by the fact that it's on the right side of the equation, don't be. Remember, if I say that x is equal to 2, I can say that 2 is equal to x. I can just switch the location of these left and right sides. It's not going to be a problem because I'm saying they're equal to each other. Okay, so now let's look at the left side. We have s plus 7, everything divided by 4. I can't simplify this other than say dividing it into 2 fractions. This is, not simplified, but this is the only thing that I could do with that left side. So now I have to match my answer with whatever's presented to me. So when I look at choice F, clearly that's not the right answer. G, it's not the right answer. H, not the right answer. Now we have J and K, and we know that it's S plus 7, so it's K the correct answer. They did not break the S plus 7 divided by 4 into 2 fractions. They could have, and so you need to know that this is equivalent or equal to that. Just keep that in mind. But in this case, you didn't have to do that because we have a match.